Welcome, everyone. It's 11 o'clock. If you are here to be involved in fractional slot concentrated windings, where and how they are used, you're in the right place. My name is Chase Fell. We're glad to have you this morning. I want to remind you to make sure and silence your phone during the session. I'll be here to help facilitate and have the microphone when we have a chance for some questions and stuff. I'd like to introduce our presenter, Mike Howell, who PE is part of our ESA technical staff. When I first met Mike, was in about 2003. We worked on a squirrel cage rotor project for a nuclear application. You guys that get involved in nuclear applications know how complicated that is. And I learned then how Mike does his work. There are things that are very complex and there's things that are very simple. And he has a way of using data and calculations and common sense to get to the right place. So anyway, if you'd like to read Mike's bio, if you go to the main menu and go to speakers, you can see that. I think that's something you might enjoy. So with that, Mike.
Thanks, Chase. When you said complex and simple, I thought you were going to say, and he's got a good way to screw up both of them. But this is a topic that will probably not be of a lot of interest to you until it is. So these are windings that they're not the run-of-the-mill windings we see every day in the shop. These are the things where we get in the machine, maybe we didn't really grasp the nameplate. It's a good customer. They want us to work on it. We're not that comfortable. And then the winder gets into it and says, this just doesn't make sense. It's kind of screwy. And hopefully it hasn't been burned out yet, or maybe the connections weren't damaged too much in the failure. But these, we're seeing more of them. They're not going to be in your 1,000 horsepower, 1250 horsepower machines. They're going to show up in generally something under about 50 horsepower, pumps, fans, some more process equipment. They've been used for a long time, fractional slot concentrated windings, but usually in much smaller machines, even something like a hard disk drive motor. So like the people from NEDAC, may be familiar with those machines. Where we're seeing them now, as far as in industrial motors, is in switch reluctance machines, which you might be seeing some of, but also in permanent magnet synchronous motors. And we're going to kind of go through an example of a permanent magnet synchronous machine. So there's some advantages to designers with using this type of winding. Another application's EVs. They're very mechanically robust, and the end windings are really short. So when you're dealing with big power density constraints, you're trying to get a lot of kW per cubic meter, then something like this might be a good option. So we're going to kind of back through some winding fundamentals and develop a winding for a machine like you see on the right that's represented with 12 stator slots and 10 rotor poles. We're going to look at some numbers that we throw around with standard lap windings and concentric windings, things winders look at every day. Slots per pole and phase, winding factors, and by that we're talking about distribution factor and chord factor. So these are things, if you use the ESA redesign program or the old blue book, you see these numbers when you go through typical windings. And then we'll talk about some tests and inspection that we can do with fractional slot concentrated winding machines that are a little different than what we might do with the typical stock induction motor. We're going to try not to go through too many crunching of boring numbers, but to put in perspective what we're dealing with. On the right, what we're representing here is a 24-slot stator. So, in an induction machine, that would generally be something really small, but the numbers work out, so that's what we're going to use as an example. If we had a 24 slot 2-pole machine, and we have all these are 3-phase, then the number of groups of coils in a 2-layer lap winding, like we see, day after day in our shop, would be 6. Poles times phases will give us the number of groups. And then if we divide that 6 by 24 slots for a 2-pole machine, we'd have 6 groups of 4 coils. That would be our lap winding for a 24 slot 2-pole machine. With a 4-pole machine, we'd have 12 groups of coils, and we'd have 12 groups of 2. We could do an 8-pole machine with 24 slots. In that case, we would need 24 groups of coils, so we'd have just 24 groups of 1 coil. If we get slots per pole per phase below 1, we have to get a little more creative. We have to use either a consequent pole winding, which a lot of manufacturers will do on smaller machines, just because it reduces the number of connections. And then when this number becomes fractional, we may have to use what we see generally in larger machines, which is odd grouping. So our slots per pole per phase is not an integer anymore. So we're going to end up with so many groups of this many coils, so many groups of that many coils. And we can do that to the point where we get down to 1/2 slot per pole per phase. But below that number, you're going to look at the number of slots, and you're going to look at the number of poles, and you're going to say, I can't make a winding to work. If I need 30 groups of coils and I only have 24 slots, there's no way to achieve that. And that's where these windings, and the way the theory works behind them, gets a little bit unusual for winders that are accustomed to working with visually symmetrically objects that make sense. So we're going to go through a couple of examples, and I'm throwing out a nod here for our internal connection book. We get requests for this every week, and the worst call is when the winder has one, and he says, well, I'm on page 12, and it says this. And I look at my page 12, and it doesn't say that. And I'll say, well, what version is it? So this one says 1986. So between 1986 and now, I can assure you we have found some mistakes, that everybody's going to make mistakes. We've got some, and we've found those, and we've hopefully corrected them, and we've added a lot of content. So go out to ISA.com, log in. This is a free PDF download. If you're using tablets out on the floor, if you're using your mobile phones or computer, all that information is available to you. We would really encourage you to use it when you don't have the manufacturer's original connection, because a lot of members use this book every day, and so we know that what's in there works. The first example we're going to go through is what we would call the conventional winding. So when we calculate our slots per pole per phase, that number is at least 1. So we have enough slots to have at least 1 coil per group with a conventional winding where we're connecting our groups north, south, north, south, north, south. We're going to go through an example of a 24 slot 8-pole. So 24 slots, 8 poles, we need 24 groups. So that gives us 1 slot per pole per phase. We'll have 24 groups of 1 coil. In the connection book, we'll have a lot of these tables. So you look up the number of poles, the type of connection you're using, and you get a template like this showing all the groups of coils with a start and finish lead. So we can choose the appropriate one. And it's like a connect the dots. So we're connecting all our groups of A phase, and we can draw arrows to indicate our polarity as we go around and verify that the polarity is alternating north-south, north-south. We'll add the other 2 phases in, and then at the end of the day, that gives us the connection that we need to use for that stator. So a finished diagram for that 8-pole machine. And when you go around and count these groups, you can count the 8 poles. It's very visually easy to see that for each phase we've got 8 arrows, and those alternate in polarity. And if you look at the 2 phases beside those, they have a different polarity. So you've got that alternating polarity that a conventional winding is going to have. And it's nice. It'll look symmetrical. When our slots per pole per phase end up somewhere between 1/2 and 1, we can no longer use that conventional winding. We've got to modify the connections a little bit to create those other magnetic poles. And in that case, we can use what we call the consequent pole winding. And again, usually that's going to be on smaller machines, although not always. So the example we're going to push through here is still staying with that 24 slots. We're going with a 16 pole machine. So we've got 1/2 slot per pole per phase. We're going to use 24 groups of one coil. So the number of groups we need for the consequent pole winding is 1/2 of what we needed for that conventional alternating polarity winding. So same thing, we can go and get all of our lead numbering and our pole connections. We'll use that same template. And this time we're connecting these groups in the A phase by having all the same polarity. So every time that we go through two groups of coils and we connect them for the same polarity, what we create magnetically is a consequent pole halfway between those two. It's a return path for our magnetic field. That magnetic field is preserved, and so what leaves a pole from the top has to return to the bottom. So when we count these poles, we see that we have 8 that are electrically wound groups of coils, and then we have consequent poles between to form the other 8 poles with opposite polarity. So we get our 16 pole machine. And our second and third phase, I'm going to skip through that, are going to look the same. And again, we can compare our connection and see that it makes sense. We have 16 poles per phase. The arrows are changing direction all the way around, so we can arrow through that. And for most winders, that's going to be a pretty straightforward connection, and it's going to jive with what they're accustomed to seeing. The other kind of in-the-middle connection, we have a few examples of this in the internal connection book, or what we have labeled in there is part salient, part consequent pole. And it's where we have a combination in the phase with some groups connected with alternating polarity and some groups connected consequent pole. The only reason the manufacturer uses this is because they've already designed a stator, they have an order for some motors, and it's cheap. They don't have to go back. It's not because you get some great performance or you're going to have the best efficiency or the lowest harmonics. This is out of just the convenience of using an existing design to meet a customer's order. So the example we'll go through here is a 24-slot, 12-pole machine. Anytime your slots per pole per phase is a fraction that's divisible by the number of phases. So if you have a 1/3 or 2/3 or something like that fraction, that's an unbalanced winding. So that means that as the EMF is generated, that back voltage, speed voltage is generated back into the winding for the 3 phases, it's not going to be the same like it should be for a balanced 3-phase load. So we're going to have a difference in the voltage that's generated in each phase, or the angle between those voltages not being 120 degrees like it should be, or a combination of the two. So again, this is not the motor you want to really brag about if you're building a one-off. This is something somebody built because of the convenience. So the connection for this is really going to look kind of screwy. We've got some jumpers where we've got alternating polarity. So if we look at the first 2 groups of this C phase, and then the next jumper is what we call a long jumper, and it skips over only 3 groups, and we have a consequent pole connection. So we're getting a consequent pole here, and if you look, the spacing is uneven. But if you go around and count, you'll get the correct number of poles here, so you'll get a 12-pole winding. And those are the 3 cases that we deal with in the service center every day. We don't see this, this doesn't happen every day, but it happens periodically. We can still do this with, a fairly conventional winding, and it kind of makes sense. When we get a machine where the slots per pole per phase is less than a half, even if we use a consequent pole winding, you're going to come up with the need for more groups of coils than you have coils. So, that becomes impossible if we're using what's called our fundamental, which is what we assume we're using on all those previous calculations in our books and things we use in our ESA materials. So where this becomes a little bit like trying to imagine something almost in another dimension is if we have a coil and we have current coming out of one side of that coil here towards us out of the page and returning back into the page here, and we have just a two-pole coil, the magnetic field that will be formed will be of one polarity, strongest in the middle of the coil here, and of the other polarity on the other side, it will be in negative at the strongest point halfway between the coil. And that's our typical two-pole winding kind of unraveled for one coil. In reality, what we've got really is more of a square wave for this one coil going around the periphery of the stator. And the first harmonic, what we call that fundamental or first harmonic, is sinusoidal, but it's the square wave is made of that plus a slew of other harmonic fields. And we can't see that by looking physically at the coils, but we can analytically come about it, on how it works and what it does. We sometimes see the negative effect of some of these space harmonics when we have problems accelerating a two-pole motor. Maybe we have a high fifth or seventh harmonic, and we get a cusping effect, a torque reduction as we're accelerating. But with the case of this fractional slot machine, the designer is going to take advantage of these harmonics. So instead of trying to minimize them, we're going to pick one that matches the number of poles we want, and we want it to be very high. So we're going to try to maximize that harmonic. So in the case of this example where we have a 12-slot, 10-pole machine, related to the fundamental, which has one pole pair or two poles, we want to use the fifth harmonic, which has 5 pole pairs or 10 poles. That's going to be what we call our working harmonic. Now, that's not going to be something we could really do with an induction motor pretty easily, because in our squirrel cage rotor, which is really dumb, right? It's going to just, however many poles we have in the stator, with a strong field, that's what's going to develop in the rotor, and that's kind of what we're stuck with. But when we use a permanent magnet rotor, what happens is if we put a rotor inside the stator and the rotor has 10 strong permanent magnets, if there is a fifth harmonic field, if there is a 10-pole field, it doesn't have to be the best in the world, but if it's there, it's going to sync up with the rotor magnetic fields. It's a synchronous machine. It's going to sync up, and that's going to be the operating point. So the way we typically lay out the three-phase windings, and we're going to kind of talk about this in terms of a two-pole machine. The way we typically lay these out is what we call 60 degrees phase belts. That's our typical two-layer lap winding. And for any three-phase source, we want a winding that has 3 individual windings, one per phase, separated electrically by 120 degrees, and in time by 120 degrees as well for the supply. When we talk about 60 degrees phase belts, what we're doing, and if for a standard two-pole winding, we would have something like this, right? We'd have 6 groups of coils. Poles times phases would give us 6, and they would be evenly spaced around the stator. So we would have a positive A phase, and then 180 degrees away, we would have another A phase group, but with the opposite polarity. That's our alternating polarity conventional winding. When we lay out the winding this way in these 60 degree phase belts, we tend to get what's called a good winding factor. Permanent magnets are expensive, right? So, and they're short in supply. So the flux that we're getting out of these permanent magnets costs us a lot of money. We want to use as much of it as possible. If we have a low winding factor, that means to get a good, strong EMF generated in our winding, if we have a low winding factor, we have to have a stronger magnet. So we want to make our coils as useful as possible. So these 60-degree phase belts allow us to do that. When we move away from the two-layer lap winding and go into this 12-slot 10-pole machine as an example, for any stator, we can say that the mechanical angle between the slots is just 360 degrees divided by our number of slots. So if we have 12 slots in the stator, then 30 degrees mechanical separates the center of these slots, or the centers of the teeth. Each one of those is separated 30 degrees mechanical. So for any winding here, the electrical angle between poles is 180 degrees. That just means that at each pole we flip the polarity. We go from north to south. So in electrical degrees, that's 180 degrees. What we're interested in when we're laying out this winding is what is the electrical angle between those slots. And in the case of the 12-slot 10-pole, we've got 30 degrees mechanical between the slots, and we've got 5 pole pairs. So 30 times 5 is going to give us 150 electrical degrees between the center of the slots. And we can see this graphically because if we look at the separation between the poles, and we know that that's 180 electrical degrees, we can see that the slot separation here is slightly less than that. So that 150 electrical for 30 degree mechanical makes sense. So just to reiterate or reinforce, what we have is a slot pitch that's almost by 150 over 180 a pole pitch. That's the separation we have there. So the method we're going to use to lay out this example winding is what we call slot star. And you can go on eBay and get you a $6.99 design book from 1912, and it's going to have the slot star in there. This is not something new that's only used for fractional slot windings. We can use this same methodology for any of the windings we put in our polyphase machines. But if we start by putting one coil over this tooth, and this coil you can imagine being very similar to a shunt coil in a DC field frame. So it's just quite a few turns of round copper, and it's installed over one tooth like a field pole. So if we magnetize this tooth by putting current through this coil, we could say that we'll have a magnetic field going in this direction. And we're choosing the direction arbitrarily, but so for slot 1, it's going to be going in this direction. Now, if we had a 2-pole 3-phase winding, the slot 2 here would be 30 degrees from the slot 1 electrically. But because we have that 10-pole winding, remember we're using that 5th harmonic, we've got 30 degrees times 5, which is 150. So coil number 2 here is not 30 degrees electrical from coil 1, even though it's 30 degrees mechanical. So we've got an electrical angle of 150. So that gives us our second coil. And what we're going to do is just work around in a counterclockwise fashion. The third coil, we're going to advance another 30 degrees mechanical, but we have to advance another 150 degrees electrical. So for our first 3 coils that are occupying these teeth, we see that their magnetic field vector would look like this. So certainly nothing that is symmetrical and evenly spaced. So we're going to keep going around just like that for the remainder of the coils. And what we have is a depleted battery in my pointer. But what we have is, we had number 3, which was right here, If we go another 150 degrees, we end up with number 4 here. Another 150 degrees, we get to 5. Another 150 degrees, we get to 6. So we just keep repeating that pattern until we go all the way around through 12. And what we end up with is an arrow that represents every coil. But if you look at the number that's assigned in the layout of the arrows, it's not real logical about the best place to energize. Oh, thank you. It's not real logical about the best place to energize those. Okay. So if we go back to our original layout where we had our 60 degrees phase belts, we've basically just taken those pie slices, 2 for each phase, and laid it over these coils. It's arbitrary. You could choose to rotate that however you want, but if you lay it over those 12 arrows symmetrically, you're going to end up with 2 arrows per 60 degrees phase belt. The only question is, which coils do you connect electrically to each phase? We want coils that are close to being in phase with one another because we want to get maximum voltage generated in that phase. So we can see that coil 1, which is physically wound over here over this tooth, is pretty close electrically to coil 8, which is wound over here at this tooth. And if we measured that distance, it would be both of them are about 15 degrees electrically from the center, from that 8+, or they're about 30 degrees electrically apart from one another. 180 degrees out from here, we have what we would assign to our A negative, and we see that number 7, which is here, is pretty close to being in phase with number 2, which is over here. And the other curious thing is that 7 is also exactly opposite from 1. So if we have 2 coils and they have exactly the same magnetic field vector but in opposite directions, all we have to do is change the current direction in that coil and they'll be the same. So if we had 2 north poles and we wanted a north and a south, we could flip one of them and then we would have 2 norths. So this group, these 2 coils over here, we're going to connect those with opposite polarity to what we connect these 2. And when we do that, we'll find that the 4 of them work together close to what we would want for that A phase voltage. And the same thing goes for our B phase, which is going to be applied at 120 degrees electrical from the A phase, and then our C phase, which is going to be applied 240 degrees electrical from our A phase. So we've got 4 coils assigned to each one of the phases. That gives us 12, and we've got 12 coils in our stator. This gives us a pretty good balance. So from that, we can develop your standard typical connection diagram. That again, if we didn't go through this, showing how these can work together and should be connected together, it's going to look a little bit screwy. Because we've got our A phase, or line 1, going in this first slot coming over. And then right beside it, we've got another coil that's in the same phase, but if you look, the polarity is opposite. That's unusual. Normally we wouldn't have that, but it's because of the 5th harmonic is what we're looking at, that 150 degrees electrical between the 2, that's going to make this all work. There's nothing else special about this connection, and we've had quite a few members that have wound these successfully without having any of the content from any of the previous slides. What did they do? They received the motor. They couldn't run it, but they could visually look at it. They duplicated what the manufacturer did. They sent it back to the customer, and it worked. And sometimes that's what is kind of required. If you get into something that's got something like 36 slots and 48 poles or something crazy like that, it's going to get quite elaborate. So we wouldn't necessarily want to go through this exercise for every winding we did, but this kind of gives us an understanding of how that machine would be laid out and how it would work. Now, externally, this is no different than any other three-phase winding. Depending on the number of turns and the applied voltage and the frequency, the manufacturer could have designed this to be a Y connection. They could have designed it to be a delta connection. In this particular winding, all the coils in one phase are in series, but they could be connected in parallel where they would not be out of phase with the other parallel circuit. So that's a possibility. So we're going to move into, now that we've got this winding laid out in a way that we think makes sense for a three-phase power supply using that fifth harmonic, we're going to look at the winding factors for this winding and see how it would perform. Again, what we really have to think about, what the manufacturer thinks about from a design perspective, is how much bang are they getting for their buck. If they're buying these neodymium boron iron magnets, with a certain magnetic field strength, how much of that is getting converted into voltage in the back EMF of the machine? Or another way to look at that is how much flux do they get per amp, or how many amps per flux to produce the torque they need for that motor. So this winding factor, which in our typical books, we usually break it up and say chord factor and distribution factor. In these types of windings, they're usually combined as a finished product and called K sub W or winding factor. But that's a measure of how effective each coil is based on being in phase with the other coils around it from the same phase, and as far as the pitch of the coil versus the pole pitch of the magnet. The first one we're going to look about is distribution factor. Now, if you do redesigns and use the ESA program for integral slot windings, it calculates that for you. It's kind of built in and you don't see it. It's out in the background. If you're still using pencil and paper in the old book, then there's a table that shows you what the distribution factor is approximately, and then there's some calculations you can crank through. We're not going to spend much time on the math here. We're going to touch on it, but we're going to look more graphically at the way that distribution factor is formed and what it means. So if we take just our 4 coils for A phase, we've got coil number 1, coil number 8, coil number 2, and coil number 7. Those are our A phase coils. We said that 1 and 7, if we just flip the direction of number 7, it's going to be exactly in the same line as coil 1. So those are perfectly in phase with one another. So up here, what I've done is I've drawn an arrow for 1, and then I've got -7, so I've flipped 7 around, and I'm attaching it to the end here, so those are in phase together. If we look at number 8, which is our third coil in this phase, it's swinging down 30 degrees from coil 1, or it's also about 15 degrees from the center of this A positive. So I'm moving it over here, and it's 30 degrees off of this line. And then our fourth coil, which is number 2 here, you can see that if we flip the polarity of it, it's perfectly aligned and in phase with coil 8. So here's the arrow for coil 2. You can see that the shortest distance between 2 points is a straight line. And if we've got these arrows, the only way they can go from here to here is in this path. Now, you could rearrange that to look a little different, but you'd still get to the same place by connecting those 4 arrows. So that's going to be our end result. That's where we're going. That's the most we're going to get. The longer this is, the better we are, because the less EMF we're going to lose when we start spinning that rotor. If we look at the departure, if we said each one of those was just, let's just say, use the number 1 for simplicity. If each one of these was 1 long, then this dimension here would not be 4. It's only going to be about 3.8. It would be this 0.966 times 4. So that's the most we'll get. and that's really what we call our distribution factor. And we can use this, if you have a scientific calculator and use this cosine function, this is a right triangle, and we can solve for that way. But the way to think about it is we want to go from this point to this point, but because of the position of these coils in the slots, we can't go straight across. They're not all in phase. So this is the path we have to take, and that path is longer than this. Another way to say that is we're not going to get everything out that we put in. So that's our distribution factor for this winding is a 0.966. And the closer we are to 1, the better off we are. So that's a pretty good distribution factor. We could have assigned any 4 of these coils to A phase. We could have made it number 8, number 11, number 2, and number 7. What would have happened there is that angle to get from here to here, those angles would have been all over the place, and we might have only ended up with an arrow this long. So we would have had a really low distribution factor. So if you look in one of the textbooks, you're going to see some crazy math like this where those angles using trigonometry are solved, and you get that same factor by doing the math there. But this is based on having a 60-degree phase belt. This Z factor has to do with how many slots we have, and then what is the greatest common divisor between our poles times phases and our number of slots. So yeah, I would not recommend sitting around calculating distribution factors by hand on a regular basis. It's not that practical. It's more important to understand what that number's telling you.
Is that related to efficiency? So my distribution factor is 1, right? My efficiency is going to be much higher than something the distribution factor is lower.
It'll be sort of related to efficiency in the respect that if your distribution factor is higher, you won't have to have as many turns in each coil to get the same back EMF. And because you don't have to have as many turns, you can use more copper in each turn and therefore reduce your winding losses. So you get more, basically more effective coils that way. So yeah, I wanted to include this on calculating that distribution factor, but again, programs will do that for you. The second component of that winding factor is what we call the pitch factor or the chord factor. This relates to how wide the coil is versus the magnetic pole. So you can almost think of a butterfly net. If your coil is the ring of that net and you run through a bunch of butterflies, the larger your net is, the more of the butterflies you're going to catch. So this chord factor has to do with the fact that there's a certain amount of magnetic flux leaving that magnet and crossing the air gap for each pole. The wider the coil is relative to the pole, so if it's exactly the same width as the pole, then all the flux that's leaving that magnet is going to pass through that coil or be linked by that coil, and you'll get a maximum induced voltage. But if you start making the coil more narrow, it's going to be linked by less and less of that flux per pole, and you're going to get a lower, what we call chord factor. So what we've got here is this 150 degrees is how wide our coil is, and the 180 degrees is how wide the pole is electrically. And this calculation will give you the chord factor. This is equivalent to losing 3.4% of the voltage that would be induced in that coil if it was 180 electrical degrees. So we want that number also to be pretty high. In our typical or conventional induction machines that we work on every day, that number is usually 0.9 or well above that, with the only exception being 2 poles. And the only reason that is because they're just become impossible to wind if we get too high on a lap winding. But it's not usually out of some desire. So we want that number to be pretty high. So once we get our distribution factor and our pitch factor, we just simply multiply those together, and that gives us the winding factor for that winding. In the land of fractional slot concentrated windings, if you get above, say, about 86%, you're usually in pretty good shape, and that's what they would call a feasible design. That's a trade-off that says, I'm going to get enough back EMF out of that winding that the layout I'm using is practical, and I don't need to look at a different slot configuration or something like that for the number of poles that I need. The distribution factor and the pitch factor that we've calculated here were based on that fifth harmonic, so that 10-pole winding. I was saying that the actual field is composed of lots of harmonics. So you can actually calculate the pitch factor for this winding for a number of different harmonics. We want, ideally, the fifth to be very strong and the rest of them to be very low. That would be ideal. But when designers go through and look at an entire machine, they'll look at those space harmonics across a number of poles to make sure that they're not going to have problems during operation with like cogging torques or pulsations and things like that. But here we've got a good strong winding factor, so that would be a feasible design. So anywhere in slots per pole per phase between 0.25 and 0.5, we can usually use that single tooth type winding in the design, and it will give us a 0.866 power winding factor or higher. When we are working on something like a 36-slot 4-pole typical lap winding, and we short pitch that coil and have a chord factor of say 0.941 or something like that, we lose about 6% of our fundamental voltage, but we can eliminate very large percentages of some of those harmonics, especially the fifth and seventh. So that is targeted. That's why we chord those standard lap windings. Okay, quickly, we're going to look here at layouts for the switch reluctance machine. You may see some of these come through periodically in your plant. For those with 3, 4, or 5 phases, the typical layouts you might see if you look at slots and pole counts, you can count the rotor poles simply on these switch reluctance machines. There's no windings, there's no magnets. So these are solely by reluctance torque and the tendency for stills to want to align at the point that requires the least energy. So the magnetic fields are going to want to align. That's how these machines work, all reluctance torque. So if you get one in the shop that has 8 stator slots and 6 poles, that's going to be a 4-phase machine. These are all operated from special drives, and you would need the drive to be able to test run the machine in your shop. If you don't have it, you can't do it. That's the way it boils down to. It is most common to see 3-phase, but that's not a requirement. It just makes the power electronics simpler. With permanent magnet synchronous machines, some common combinations. So in this case, we're always going to have a number of slots that's divisible by the number of phases. And with these all being 3-phase machines, at least in these tables, here's some known working conditions. So if you find a 12-slot stator, it's probably going to either be an 8, 10, or 14 pole. And in the case of the permanent magnet machine, you can certainly count those poles easy enough. Any place in this table you see a star, that just means the winding factor is above 0.9. So, if I'm a designer of these machines, those are the ones I'm going to tend to use because they're right off the bat more effective. If you find something in your shop that doesn't fall in these lines, so if you find a 12 slot and you count 20 magnets on the rotor, give us a call because something's a little screwy there. They may be using a different topology than what this is based on, or it could be a different number of phases than what you're seeing with a 3-phase. We're going to touch on some of the tips for working on these in the shop, and specifically around here on the permanent magnet synchronous machine. Like any permanent magnet rotor machines that you receive in the shop, recommendation is to remove that drive-in end bell, have the machine vertical shaft up, and use your crane to lift the rotor out. There's usually a really fairly good magnetic balance there, so you can pull it out without a lot of worry of contact between stator and rotor, providing you're lifting it vertically above. Same practice can be used to install the rotor back in. Never put your hands or fingers or anything like that, certainly in the way of the rotor and any magnetic steel materials or the stator. Outside of that, most of our standard cleanup and refurbish type jobs, we can do these the same as we would do any induction motor. So replacing bearings, checking journals and housing fits and all that good stuff, we can do that kind of work the same way. If we rewind one of these machines, we need to rewind it in kind, meaning as we found it. We have to be concerned about the insulation class that's indicated on the nameplate. So the advantage of this type of machine is you can work at fairly high torque levels at low speeds. So they can get, pretty toasty. So you want to, you certainly don't want to put a Class F winding back in a Class H nameplated machine. We want to pay attention to our rated terminal voltage, make sure the insulation system you're using is rated for that voltage class. This is a 12-slot 10-pole machine. It's a 75 kW compressor motor. Runs at 3185 RPM. One of our members rewound that. Don't ever be afraid to contact the manufacturer. The word proprietary exists, but they're oftentimes going to be willing to share with stuff like this. Number one, if they're pushing this product out, it's not they're not building them by the millions. So this is something that they're trying to get out in the market, and they want success. They want the customer to be happy with the lifetime of that machine. So they may be willing to help you with the repair of it and provide you things like connection diagrams, bill of materials, test and inspection procedures. You can get all kinds of stuff. This is a 7.5 kW, runs at 2300 RPM, 12-slot machine. It's a pumping application. But reach out to the manufacturers always for that type of material. Now this is one area that can get us into trouble, especially with delivery time. You need to inspect these coils very carefully because we're operating with, these are all inverter-driven machines, and they operate at fairly high frequencies, and sometimes the number of turns per coil is going to be a pretty low number, which means the turn itself is going to be pretty big. And if you do a lot of large form-wound like generator coils, you'll see that the laminating of those turns, even at power frequency, is done to reduce eddy current losses and circulating current losses that you can experience. When we're in these cases of sometimes being up into a couple of hundred hertz, that can be a severe condition. So what you'll see sometimes is use of what's called Litz wire, which it just means stranded, but intentionally stranded. So it's not just getting 15 wires in hand. These wires have a pattern throughout the bundle that they're manufactured with. The benefit there is we reduce those eddy current losses, which gives us lower temperature rise. If we don't replace it, we're definitely going to overheat, and your customer's going to be unhappy because the machine is going to fail. There's a couple of suppliers of Litz wire in North America, and there's a couple in Europe. Just a web search using your favorite search engine will find you those. There was a service center in Canada that actually built essentially an add-on machine to their winding machine that allowed them to essentially produce their own Litz wire. I don't know how well it turned out, but I did see a video of it kind of in service. If we kind of zoom in, this is what you might have. So there's different, when you look at the Litz types, you might see type 1, type 2, type 3. So there's different types of stranding. This one here has 37 strands of 23 gauge. So you may have 1, 2, 3, 4. Here they have 5 bundles. So all those individual bundles are also then twisted. You can see like the roping of that. And that's going to significantly reduce those losses. So don't make the mistake of not replacing that Litz wire if that's what you find. AR100, you can use those same tests, the tests we use on all induction machine windings on these machines as well. I mean, we're going to look, we have, at the end of the day, we've got a balanced 3-phase winding. So we can do things like compare coil resistance. We can measure line-to-line resistance and look for balance there. Insulation resistance test, use the 500-volt megger for the voltage class you'll be dealing with here and correct that value to 40 degrees C. New windings need to be hypot tested, twice rated plus 1,000 for 1 minute or 70% above that for the DC test. If you're refurbishing one of these machines and you need to hypot it, you'd use a 65% multiplier for aged windings as long as they're clean and dry. If you have a 3-phase machine, your surge test should be meaningful. If you're working something like a 5-phase switch reluctance, the surge test is not going to be all that helpful for you because you can't. Your test equipment's just not built for it. But we can also individually surge test these coils just like you might an interpole or a series field coil or something like that in your shop. Impedance testing, where we pass a low voltage AC through the coil, measure the current, just compare each coil. You could do something like that as well, just to have some kind of indication that you're not dealing with a turn short. With permanent magnet synchronous motors, these aren't self-starting, right? So with a large wound pole synchronous machine, we would have a damper winding in those pole faces that would allow it to start as like an induction machine. The only way to get these up to speed is to have an inverter so that we can basically lock in the poles at very low frequency and then accelerate those up together. So you would need a drive. We can check our rotor here by measuring the open circuit volts per RPM. So if we're driving at base speed, we should have a terminal voltage that's slightly above the base voltage on the nameplate. You're going to get really low magnetizing or no load amps because the magnetizing current or the flux for magnetizing is provided by our permanent magnets. So we don't have that low power factor condition, no load. A lot of shops that do have VFDs now and run inverter duty machines in their shop, some of our members have had success running these machines in their shop and some have had difficulties. Without going into a lot of depth, it may depend on how they have their drive set up and the capabilities of that drive for that machine, but you can oftentimes run these in the shop. The switch reluctance machine, in this case, there's no drive that you are going to have in your shop unless you got it from the manufacturer or from your customer. These are going to be special tuned specifically for that machine and the correct number of phases for that machine that you're testing. So this is a switch reluctance motor, 45 kW at 1800 RPM. The only way you can test run this is by having that equipment. So you would be stuck with doing your mechanical and electrical testing and basically doing what you can do, and your customer needs to know that up front, and then you'd have to do some startup testing and make sure everything's good once you get back into service. Do we have any questions, comments, or anything for these machines? Are any of you seeing these in your shops? Okay. Yeah, that's what's happening. I mean, I've been with these for 10 years, and we're seeing more and more of these now that we're starting to get enough of them to have pictures and all that good stuff. So.
Last Friday, poured on 2 servo motors. Pretty sure. By the way, the salons are. The windings are completely encapsulated with that hogging.
Yeah, so even some of the machines that are used in that type of application where the switch reluctance machine is also sometimes called variable reluctance, but it's very similar in construction to a stepper motor. It's just instead of position control, we're using it for continuous duty, but you'll see that same type of winding.
Is it also similar to like ECM motors used in like airplane equipment?
Yeah, those more of the pancake stuff. Some of those are. You're talking about the real narrow.
Well, there's some that are like pancake style, and there's some that are more like blower motor in a residential HVAC.
So some of the more conventional builds, so the HVAC stuff is what's going to be called BLDC or brushless DC, but it will have sometimes some similar windings to this. Other times it'll have just more of a conventional three-phase, but it's what we call an electronically commutated winding. That I couldn't afford that when I replaced my HVAC stuff at home. I was disappointed. But
don't be disappointed.
Yeah.
They're real sensitive.
Oh, well, thanks. You made me.
Electrical surges and stuff.
My wife appreciates you saying that. Thank you. I appreciate it.
So great presentation, good information. I appreciate that. That's great. So how about tips for making up coils for shops? Because I know a lot of the examples you were showing there, they had pretty generous slot openings, and the wedges were pretty large. But I've seen, especially when you get the smaller ones or maybe traction applications, they'll have pretty small slot openings, and the way they're manufactured will be with individual poles. But once you get them, they're bonded, they're welded up, and it's not like a field pole where you can pop it off and wind it on a form or something. So any good tips on making coils up in slots or that might have a little bit skinnier opening?
With the traction style small applications, what I'm seeing more of is pin style coils. They're rectangular wire, and I don't know. And correct me if any of you are repairing those. I've seen that be more modular replacement by the manufacturer, and I'm not aware of our members doing a lot of repair on those yet. Now there may be somebody that's found that to be their bread and butter already, but I haven't come across it, because you're right. There's an incredibly limited amount of space available, and those can even take on the form of even a 4 and 5 layer winding with a lot of special connections. So they're generally using induction brazing with special fixtures, and that's the one you want to farm out to your competitor or send them down the road. I think right now, anyway.
We probably got time for one more question.
Do you, as from ESA, do you all see that the industry is going to be headed this way? Because there's some indication that we're going to see more and more of this, like double in the next 8 to 10 years. Is that what you're all seeing?
I would say that the number we've seen in the last few years has certainly doubled and tripled. There's still a small portion of what we see, but enough of them that I thought it would be worthwhile to share some information on the connections. Usually, when we hear about these, it's usually somebody's rewinding and they're lost on the connection, or they just put them back in and wound them alternating pole, and now it's not working. It's that kind of thing. So I do think you're going to see more and more of them. One of the other advantages of this type of winding is when you have a 3-phase winding and none of your phases cross over or contact each other. When you have a phase-to-phase fault, it's very fault tolerant. And some of the ones that are made with 5, 6, or 7 phases, they can actually even have a drive that fails on one phase completely and kind of limp along and work. So they're fault tolerant for those types of applications. Thank you. All right.
Thank you, Mike. Thank y'all for participating. It's really very interesting. It's about all the time we have.
Thank you.